All right, you guys, I am going to tell you about the wonders of water. Water is really a miracle. We wouldn't be here if water didn't have a lot of very unique and special properties. So what I'm going to suggest that you do as we kind of go through these slides is make a list. Get a piece of paper and a pencil and just start kind of making a list of some of these amazing properties. And what I'll do is I'll do the same thing and then we can kind of talk about it. All right, now if you look at this, remember why atoms come together. Atoms come together to fill outermost shells and also to neutralize charge. And so if you look at the water molecule, better known as HOH, a lot of people get mixed up. It's H2O. There's two hydrogens and an oxygen, but sometimes I just have my students say HOH because then they kind of know how it's configured. And you can see that these are covalent bonds. They're sharing outermost electrons and faking each other out to think that they're full. They're outermost electron shells. Now, this should be neutral, but it's not. And it has to do with the kind of the weird orbit that only holds two, that first orbital shell. And so what ends up happening is that the water is what we call dipolar or bipolar. It's charged. So that should be the first thing you write down there. Dipolar, bipolar, or charged. It's got a more positive end and a more negative end. The oxygen end is the more negative end. The hydrogen side is the more positive side. All right, this is just three different ways of showing water. You guys, you're not ever going to have to come up with the left-hand one or the center one. But if you just kind of remember HOH, that'll help you with the configuration. It's got that strange 105-degree angle, making the two hydrogens kind of concentrated on one side. That's the positive side. And then oxygen's a really negative atom, when it's by itself, and so that ends up being the negative side. So if you kind of can remember the right-hand side, you're in good shape. All right, because of those positives and negatives within that water molecules are actually really attracted to one another. And you can see that the hydrogen end on one of them is attracted to the oxygen end on another one. Now these are weak bonds, compared to the covalent bonds holding those actual molecules together, and they're called hydrogen bonds. But you gotta be careful, they're not that weak, and in fact they're going to give water a lot of its special properties. So it's dipolar, it can form hydrogen bonds, which are these bonds between water molecules. Now this is what causes surface tension. You can take a glass and actually fill it above the brim because water is very attracted to itself. You've seen a water strider walk across the surface. It can only do that because of surface tension. You could actually, if you're very careful on that overfull glass, you can balance a very thin needle. Again, taking advantage of that surface tension. And surface tension is caused because water is more attracted to another water molecule than to the atmospheric gases. All right, so we got the polarity, and we got to remember, we've talked about this before when we talked about chemical weathering, about how water kicks butt. It kicks some ionic bond butt. If you throw a beautiful ionically bonded mineral into a bucket of water, it's gone. It goes into solution. And so the next thing you need to remember is that water is the universal solvent. It will dissolve any ionic bonds. All right, so I have a beautiful halite crystal, a table salt crystal, that I've been carrying around for 20 years, and you can bet I'm never going to throw it in a bucket of water. In fact, if I'm taking it out in the rain, it gets its little Ziploc baggie because I don't want it to go into solution. I love that thing. And so if you were to take your beautiful halite crystal and throw it into the water, the chlorides would be surrounded by the positive end of the water. You can see it there. And then the sodium, the positive ion, would be surrounded by the oxygen end or the negative end. And that's called hydration. And water will rip apart ionic bonds. In the case of sodium chloride, you might say, well, why isn't the sodium and chloride attracted to one another? And they are, but they're like 80 times more attracted to the water than to each other. And so until that water leaves the equation through evaporation or something like that, the sodium and chloride are not getting back together. All right, think about this, you guys. Especially recently, I have seen water in all three phases. I see it regularly. Y'all take a nice hot shower, right? I hope. You steam up the mirror, that's water vapor, and there's been snow and ice out there. And so this is something that's pretty miraculous that it occurs in all three phases. Naturally here at the Earth's surface. I can go into a lab and put things under, extreme conditions that you don't find on Earth's surface and, make other things do this. But think in a typical day, you might actually see water in all three phases. So remember what states of matter: solid, liquid, gas. We've talked about this before. Water as a solid is ice. Water as a liquid is liquid water, and then water as a gas is water vapor. And this is kind of interesting. This has to do with energy levels, and it actually has to do with those hydrogen bonds. So we'll talk more about that. All right, kinetic energy. You guys all know that if you take a thermometer, it measures temperature, right? If you stick a thermometer in some water with ice, it's going to read a low temperature. If you stick, a thermometer in boiling water, it's going to read a pretty high temperature. And so basically the different phases represent kinetic energy, or its wiggle, how it can wiggle. And water vapor is the highest kinetic energy. And when water is in a solid form, it's in the lowest kinetic energy. In fact, it's got such strong bonds that there is no wiggle room. So if I want to take ice and change it over to steam, I just add energy or add heat. And if I want to take steam and change it into ice, I would actually remove energy. All right, so this is a great shot. Look on the far left. You guys, remember, we're going to talk about this again, but when water freezes, it actually expands. Ice floats in liquid water. And it's something that's not normal, and that's, again, going to be one of our bullet points. But the reason for that, if you look at the far left, is because of those hydrogen bonds. There's that six-sided or six-molecule structure of water hooking up through those strong hydrogen bonds. And this is kind of like taking something and putting it in a straitjacket and hog-tying it. It cannot wiggle. There's no wiggle space. A solid is very low energy, low kinetic energy, because there's no wiggle space. Now let's say I add energy. What I'm doing by adding energy is I'm actually breaking some of those hydrogen bonds. So look at the middle picture. Not all of the hydrogen bonds are broken, but enough are so that now these water molecules can slide over each other freely, and now it's a liquid. Okay, let's add some more energy. And when we take liquid water and take it over into water as a gas, what we have to do is actually break every single hydrogen bond. And that takes a lot of energy. We're going to talk about that again. And so if you look at the far right picture, you see water in its gaseous form, very high energy. It's all spread out, so kind of lower density, and every single water molecule is now completely separated. It's too high energy to make those hydrogen bonds. So, pretty neat stuff here. All right, heat capacity. Now this is a lot more simple than it looks. Now you guys, if you want to heat up water, it actually takes a lot more energy than if you wanted to heat up a rock, and I'll show you the actual numbers for that. Now, the amount of energy that it takes to heat up water, 1 gram of water, is it takes 1 calorie of energy to heat 1 gram of water 1 degree Celsius. And we are back into the Celsius, into metric system, because it just works so well. The numbers are easy. 0 is freezing for Celsius, and 100 is boiling for Celsius, and it's just a lot easier to kind of think about this. Now you might not think 1 calorie is a whole lot of energy. It's going to take, I don't know, a fifth of that to heat up a rock. So rock will heat up and cool down much faster, and that's going to really change things here on Earth. The water, the ocean, absorbs a ton of energy before the temperature rises, and then it also releases a lot of energy before the temperature starts to drop. All right, so it has a very high, water has a high heat capacity. We're going to learn rock has a low heat capacity. So again, it takes a lot of energy to heat water up. Now, this is a real quick slide to look at. Granite, okay, there's our typical continental rocks. It only takes 2/10ths, takes 1/5 the amount of energy to heat up rock that it does to heat up water. And you can see alcohol and gasoline, but we're really kind of interested in continents and ocean. And so the oceans will accept or absorb 5 times as much energy before the temperature changes than the continents will. And this is going to cause some interesting relationships. So continents are going to heat up and cool down much, much faster than the ocean. All right, this kind of matters now. I grew up in Santa Barbara, and so if we went down to Santa Barbara, and then we went inland to like Needles, California or something, give me a summer day in Santa Barbara any day. It's like always 70, 75 in Santa Barbara. And the reason for that, in the same way in Monterey, you've got a pretty stable climate is because you've got the ocean. In the summer, the sun's beating down on the continent and the continent's heating up. But right next to Monterey and Santa Barbara, what you have is the ocean, and the ocean's absorbing tons of energy before its temperature rises. And so it's like having an air conditioning unit. Now let's fast forward to the winter. In the winter, the land cools down really fast, but the ocean gives off a lot of energy before it starts to drop in temperature. So it's like having a little space heater right next to you. So think about Death Valley. You guys do not go to Death Valley in the middle of summer. It is so hot. Because they don't have the moderating effect of the ocean in Death Valley, the highs are really high and the lows are lower. But boy, especially those highs. Okay, so this is called a maritime climate, and so if you have a choice, it's always better to live someplace with a maritime climate, just because the climate is much more stable. The temperature range between the hottest days of summer and the coldest days of winter is much less. All right, latent heat. Latent heat is actually hidden heat, and it's energy that has to be pumped in to change phase. Okay, so it has to be pumped in or released, but we're going to really concentrate on going from solid to liquid and then liquid to gas. And when you go from solid to liquid or liquid to gas, you add energy. But when you go from gas to liquid or liquid to solid, you actually release energy. And that's going to be pretty important because this is how we transfer energy on the Earth's surface. All right, so let's say we have boiling water. Now, if you guys have ever accidentally left a pot of water on to boil, it actually takes a lot of energy to boil that pot dry and to get everything changed over to water vapor. If you were camping and you had just a little propane tank, you'd probably run out of propane before you actually got rid of all that water. And so what happens is that when you have water at 100 degrees Celsius, it's rapidly boiling, all we have to do is we have to change phase to steam at 100 degrees Celsius. And they will measure the same, temperature. It's just they have to go through this phase change, and it's going to take a lot of energy. Now, really quick, remember what solid looks like. Solid is where you have those hydrogen bonds all in that 6 kind of water structure, and it's really rigid. Now when we add energy, we break a few of those, we give it some wiggle room, and you can see the liquid. It's not all of them are broken, but enough are broken that now it can kind of slide past each other. And I think the definition of a liquid is that it will, take the shape of any size vessel you put it in, and that's, its ability to kind of slide over the water molecules. And now to go from liquid to gas, you've got to break every single hydrogen bond. And I said before they're weak, but you know what? They're not that weak because it's going to take a huge amount of energy to break every single hydrogen bond. All right, this is not as bad as it looks. Let's just kind of go from A to B. So we see A to B, we're going to go from solid ice to liquid water at 0 degrees Celsius. Now go make yourself a big glass of ice water and leave that ice in there a long time and put your thermometer in your ice water. You should be able to get your water to 0 degrees Celsius or 32 degrees Fahrenheit. And you'd be like, well, wow, it's not ice, it's liquid. And what I'm trying to prove there is that your ice will be 32 degrees Fahrenheit or 0 degrees Celsius, and so will your water. Now, remember latent heat. It takes 1 calorie of energy to raise 1 gram of water 1 degree Celsius. So if I pump in 100 calories, you go from B to C, and I'll take that water up 100 degrees Celsius. But look at that big flat line. Those plateaus are that hidden energy. You have to put in a whole lot of energy. You guys don't have to know that number, but it's a huge number. It's about, what, 7 times as big, 6 times as big as the amount of energy you have to do to take it from solid to liquid. And this is really important because water is evaporating like crazy over our oceans. And that's a huge amount of solar energy being absorbed, and basically, when it goes up, the water vapor goes up into the clouds, it's a potential energy source. So to get the water at 100 degrees Celsius over to water vapor at 100 degrees Celsius, you have to pump in an extra 540 calories per gram, okay, per gram degrees Celsius. So that's pretty important. Now, obviously, ocean water doesn't boil, and that's because of another miracle of water in that it can share energy, so it never has to boil. And so in reality, when we're talking about ocean temperatures, they usually don't get any more than 80, 85 degrees Fahrenheit. You're actually even talking about a bigger number that's going in here, so even more solar energy that's going to be saved up. Now, why is that important? Because every time it rains on you, we're going to have the arrow going the other way, from D back to C, and every time it rains on me, I always think about, wow, this is energy being released. So it's going the opposite way. So think about Seattle, where it rains every day, and it rains a lot. That's actually energy coming from tropical latitudes. And being released up in higher latitudes. So this is why this is important, you guys. So high latent heat, especially as you go from liquid to gas, and then that's absorbing the energy, but when you go from gas, water vapor, to liquid water, you are releasing the energy. All right. Energy transfer. Can't say how important this is. So important. You have latitudes that, again, if you guys don't like rain, don't go to Seattle. Don't go to the equator. It rains every day in the equator. And if you do like to bake yourself in the sun and be hot, go to the tropics, go to Cabo San Lucas, because that's the evaporative latitude. So tons of water is being evaporated out of the oceans, putting up into the clouds, and then because of atmospheric circulation and ocean circulation patterns, that energy is going to be released up in the higher latitudes. So this whole idea of energy transfer is so important, because if we didn't have this, the tropics and equator would get hotter and hotter and hotter, and the temperate and polar regions would get colder and colder and colder. And that's not what's been going on. It's been this beautiful, it's almost like trickle-down theory in economics. It's working beautifully, oh yeah, until humans come and mess things up. Okay, you didn't think you could get away from density, did you? Density makes the world go round. It's going to be on every single exam. Density is mass per volume, or how heavy something is for its size. And pure water, okay, we'll add salt later, but pure water has a density of 1 gram per cubic centimeter. Now, what's kind of interesting about water is that if you have a refrigerator, you guys, and your refrigerators, you do have a refrigerator. If you have a refrigerator that's working very well, your refrigerator should be 4 degrees Celsius. Okay, and mine's metric. So when I look in my refrigerator, if it doesn't say 4 degrees Celsius, I worry. Now, if you put a bottle of water in there, you're going to have water at its absolute densest. Once water cools, below 4 degrees Celsius, that's when those rigid hydrogen bonds start to form, and so it actually expands. It becomes less dense. Let's look at this slide. Okay, so what we have is, you think about most things as they cool and they go from a liquid to a solid, will obviously become more dense. That's just the way it works. Water doesn't do it, and that's one of the miracles of water. It's why we have life. But as water cools to that magic 4 degrees Celsius, it will become denser. And so water is its densest at 4 degrees Celsius. But look at the pictures D and E. What's happening is water cools below 4 degrees Celsius as we're setting up that rigid structure. If we could put all humans on Earth and put us shoulder to shoulder, we actually would only occupy, 50 square miles. It's kind of scary, even though our population is so huge. But we couldn't live like that. Now let's pretend somebody didn't take a shower, so we all have to have arm's length apart. Okay, then we're going to be, occupying a much, much larger area, 10 times larger or something. And so that's kind of what happens. It's kind of like the arms go out and we stretch things out. And so when water changes phase from liquid to solid, it expands by almost 10%. And you can see that in that picture shown as E with the 0 degrees on top. So water being less dense as a solid is something that's very different, and that's because of the hydrogen bonding. And if you think about it, lakes freeze on top. They don't freeze from the bottom up. And I don't know if life could live, and people go ice fishing. Yeah, I don't think life could live if it froze from the bottom up, if it didn't do from the top down. All right, so again, water is its densest at 4 degrees Celsius, about what your refrigerator is. And below that, it actually expands. All right, so that's pure water. Everything we've learned is going to kind of stay the same, except we've got to add some dissolved substances, some sodium, some chloride, some potassium, some calcium, some carbonate, a whole lot of different stuff. And it's going to change things just slightly. Obviously, the density, the more salts you have in it, the denser it actually is. It's going to boil at a higher temperature. It's going to freeze at a lower temperature. So things like that. All right, if you went to the ocean and got 1 kilogram of seawater, that's about 2.2 pounds, and then you put those little, evaporative lamps on it, you would end up with about 35 grams of salts, dissolved substances, after all the water was removed. So it's about 3.5% by weight dissolved substances. And it's kind of weird when you think about that, because when you taste that water, it sure tastes salty. Now, oceanographers don't talk about percent, we talk about parts per thousand, but I'll take 3.5%, that's the same thing as 35 parts per thousand. Okay, and so that would mean that 965 parts per thousand is pure water, but it's still, you can't drink salt water. You guys are ocean water, it'll kill you. Now, remember, I will ask you, what are the major dissolved constituents? It's chloride, so Cl minus, and sodium, Na plus. Not together, not sodium chloride. They are being pulled apart. Remember, no ionic bonds. Water pulls those apart. All right, what else is in there? You cannot just go to your pantry and pull out some table salt and make a saltwater tank, because there's so much more. If you ever go in a pet store, pick up a box of that Instant Ocean. If you don't live near the ocean and you want to make a marine tank, aquarium, you've got to get the right mixture. There's sulfate, there's magnesium, there's calcium, there's potassium, there's carbonate, there's so many other things in there, a lot more ingredients. Chloride's much more concentrated than the sodium because it's not all coming from sodium chloride. There's sodium in igneous rocks. There's chloride also coming out of volcanoes along the seafloor in the mid-ocean ridge system. We've got a lot of volcanoes. All right, so where did all those dissolved substances come from? If you remember, the ocean started fresh and became salty over time, and it came from weathering rocks. Okay, mostly continental, but obviously weathered rocks on the seafloor also. And chloride's a little higher than we would expect because that's what comes out. A lot of chloride comes out of volcanoes. And if you think about those underwater volcanic mountain chains called mid-ocean ridges, we got lots of those in the ocean. All right, now this is kind of something that might be hard for you to understand, is about chemical equilibrium. The amount of dissolved substances in the ocean is a constant. And that's because the ocean's been around for about 4 billion years. So when you think, well, wait a sec, sometimes the water is more salty or less salty, it's not from adding and subtracting salts, it's from adding and subtracting fresh water, H2O. Okay, so there's something called residence time, and you might say, well, why is there so much chloride, why is there so much sodium, and why is there so little like iron? Iron's really necessary for photosynthetic plants and that live in the ocean or photosynthetic algae. And so if we could actually add more iron to the ocean, we might have more photosynthesis, and photosynthesis pulls carbon dioxide out of the atmosphere. So again, a lot more complicated than I'm telling you about. But why is there so little iron? Because when an iron molecule or atom enters the ocean, it is removed within 200 years. But when a sodium ion enters the ocean, it takes about 260 million years to be removed. It's called residence time. I'm probably older than a lot of you guys, and I was born in California, so I have a longer residence time in California. There's more of me in the system because I've been here longer. So it's cool. I could explain it to you if you come in and want to talk about it more, because it is interesting. But so sodium and chloride are the longest in the residence time. And how are they removed? They're probably removed from rock forming processes or something like that. All right, so it's not the amount of salts that is changing, it's the amount of fresh water. And obviously, let's say you have a cup full of water that's a little salty to you. You go and you pour a bunch more fresh water in and you dilute it. And that's exactly what happens in areas where sea surface salinities are lower. You're adding water through natural processes like rain, precipitation, runoff from land. If you've got a big river coming out of, into the ocean, the water is fresher. icebergs melting, and sea ice melting. These all add water molecules. All right, if you've ever been in the tropics and you go scuba diving or snorkeling and you get some of that water in your eyes, like, ow, that hurts, it's so salty. And remember, the tropics are where you have a lot of evaporation, and evaporation only takes fresh water, H2O, out. It doesn't take the salts. Now also when we form sea ice, when you form ice, you guys saw that structure, that rigid six water ring structure. There's no room for sodium or chloride in there. It leaves them behind, leaving that water saltier because you're removing water molecules. All right, let's look at just some different salinities. The open ocean, it ranges between 33 and 38 parts per thousand, but it's averaged about 35 parts per thousand. Some of our large seas are actually what we call brackish. They're a little bit salty, too salty for us to drink, but fish and stuff can live in them, and the Baltic Sea is an example of that. Hypersaline, when you're more than that 35 to 38 parts per thousand, the Red Sea, it actually does have life in it, but it's a little bit more salty. It's very narrow. It's in an area of high evaporation. All right, then we get into the places where you don't have fish life. You do have weird life. You have bacteria and other weird things. Well, monolake, actually monolake is about 90 to 100 parts per thousand. If you don't have a cut and it's the summer, someday you should go float in either the Great Salt Lake or Mono Lake. You bob like a cork. The water's much more dense. Okay, Great Salt Lake, that's quite a bit more. It's almost 10 times as salty as the ocean. The Dead Sea, I haven't been there, but the Dead Sea is 10 times saltier. And so, again, you go there, and even if you're somebody who's really skinny and scrawny and you sink in water, you're going to bob like a cork because that water is so much more dense. All right, tap water, the stuff coming out of your tap has dissolved substances in it. And boy, if you're like me, I have a well and I live out in the country. I have to have a special filter because, man, do I have a lot of dissolved substances. They're okay. I mean, they're natural. They're calcium carbonate and iron, but they leave spots, and you don't want that. Now, even premium bottled water, Avion, has dissolved substances in it. All right, you guys, we're going to talk about sea surface temperatures, and it's kind of, logical. If you have a brand new wetsuit or dry suit, you're going to want to go in cold water. If you want to go swimming in your just bathing suit and not be cold, you want to be in warm water. And if you think about where warm water is going to be, it's going to be in the equatorial or tropical regions, the low latitude regions. Okay, cold surface waters are going to be in the higher latitudes, off Seattle, off Santa's Workshop, etc. And those are called high latitude regions. So you got to understand latitude and longitude in this class. And the reason that those low latitude regions are warmer and their sea surface temperatures are warmer is that they're going to be receiving a lot more solar radiation. Those are the areas where the sun's energy is really, really concentrated. All right, so low latitudes, equator, tropics, you're going to have high surface temperatures. In fact, sometimes, that water sure feels good. It's like a bathtub. Sometimes it's not at all refreshing. The water's so warm. Now, deep water is very well mixed. And so, below 1,000 meters, what you're going to find is, seawater is all going to be 2 degrees Celsius. First of all, you guys, if you're swimming, you're never going to get anywhere near that 1,000-meter mark, and you'd have to be in a pretty nice submarine to do that. So what we're going to talk about is open ocean temperature, and the next slide is going to kind of talk to you a little bit about this. Now, on the left-hand side, look at over here, temperature. You can see the higher numbers, 24 degrees. That sounds pretty good to me. Surface temperature, and that's in our low latitudes. Now, there's a region of rapidly changing temperature between 300 meters and 1,000 meters. Now, once you get below 1,000 meters, no matter where you are, the ocean is uniformly cold. Now, this is open ocean, you guys, deep water, but we've all felt this. If you've ever kind of dove into a lake, in the summer, and sometimes you're bobbing around and your feet are in freezing cold water, down deep, and your head's up in this warm surface waters. And so, in shallower waters, I feel this a lot as a diver, kind of even diving just off the coast. In those shallower waters, this can get much more shortened. You can feel this again in lakes too. But in the open ocean, this is what it looks like. Those surface waters, like the first couple hundred meters, are toasty. Then you have this region of rapidly changing temperature. It's called the thermocline. Okay, then you get down to that uniformly cold deep water. All right, let's think now about diving off British Columbia. Brr! no warm surface water. You don't have a thermocline. What you have is what I call, sorry you guys, it's a little bad taste, but butt cold water, okay? And it's butt cold at the surface and it's butt cold at depth. And you have no thermocline. And this thermocline is going to be important because with the different temperature, we're going to have different densities of water. And we're actually, where you have a thermocline, you're not going to have water moving up and down really easily. On the right-hand side, in high latitude regions, we actually can have water move up and down. We don't have a density barrier because the thermocline is going to be in the same exact area. We have something called the pycnocline, or the region of rapidly changing density. All right, you guys, so water is just a miraculous thing. It is our best friend. It's been, humans, we've been, since the Industrial Revolution, we've been kind of trashing the earth. And the ocean has done a lot to kind of suck it up for us and buffer it. But the ocean has really kind of reached its limit. And so, all these beautiful patterns that I can talk about that have happened in the past, they're starting to change. And it's getting a little scary for someone like me because they're changing rapidly. So, the fact that water makes those hydrogen bonds, has high heat capacity, high latent heat, etc., it's been our best friend. It's absorbed a lot of heat energy, but it's reached its limit. And so, if we don't change our ways, these global climate changing phenomena that we have going on could be happening much more rapidly, and we need to definitely do something different. So it's your generation, your children's generation, we got to make a change. All right, now I have a movie that goes along with this, kind of explaining this. But what this is, again, you guys, I love diagrams like this. Latitude, 0, the equator. Okay, 22 to 30 is the tropics. 60 is, 60 north is about, Seattle, British Columbia. So temperature, you guys look at the temperature. Not surprising that you're going to have your warmest areas in the equator and tropics, and then as you move towards the poles, it's going to get colder. Now, what is a little different though is this is the salinity. The blue line curves mark sea surface salinity. Okay. And it's not completely symmetrical because remember in the northern hemisphere we have a lot more land, in the southern hemisphere more ocean. So what we have here is we've got kind of two peaks at the tropics, and we have a little dip there at the equator, and then boy, we've got big dips when we get up into the higher latitudes. Let's talk about this. Okay, let's talk about the peaks at the tropics. What's going on at the tropics is a whole lot of evaporation and not much rain. And so remember, what evaporation does is remove water molecules. When you remove water molecules, you leave the surface waters more salty. All right, is it hot in the equator? Yeah, it's hot at the equator, but it rains every day at the equator. So yes, it evaporates every day at the equator, and then it rains right back down, that H2O. So that's why we have that little middle dip at the equator, because precipitation or rain is about equal to evaporation. All right, let's go to 60 north. Let's go to Seattle and British Columbia. It rains every day. And you know what? Even on a sunny day, it's not very concentrated sun. And so what happens is that evaporation doesn't happen much, and precipitation happens a whole lot. And every time it's cloudy, that's less sunlight that's coming in to evaporate. So precipitation is so much greater than evaporation that you have much, much lower sea surface salinities. All right, make sure you watch that movie. I walk through that. Okay, and again, it's a relationship between evaporation and precipitation. Where evaporation is greatest is where it's going to be the saltiest. Where precipitation is greatest is where it's going to be the freshest. And it's not adding and removing salt, it's adding and removing H2O. All right, density. We already learned for pure water that its density is 1 gram per cubic centimeter, but seawater is different. We're gonna, change its density a little bit, obviously by adding dissolved substances. But just like your salad dressing is layered according to density, just like the earth is layered according to density, the ocean water can be layered according to density too, with the lightest stuff on the surface and the heaviest stuff down deepest. Now, 2 factors that really affect seawater density is the temperature. Okay, cold seawater is more dense. So cold water of any type is more dense than warm water. So warm water would be at the surface and colder water deeper. The other thing though is salinity. The higher the salinity means the more dissolved substances you have. and that means you're more dense. And so saltier water is more dense than fresh water. In fact, a lot of times fresh water will just sit at the surface until it gets mixed in. So if you had heavy rains and no wind, you'd actually have a layer of fresh water until it got mixed by wind or current or waves. All right, so temperature has the greatest influence, with cold water being more dense, and then salinity is going to play an important role too. Saltier water is more dense than fresh. All right, so remember that thermocline that we were talking about, where you had warm surface waters. Warm surface waters in those low latitude regions, they're warm, they're less dense. That's why they're on top. Then when we got deeper than 1,000 meters, we had uniformly cold water. Cold water is more dense. And so those where you have a thermocline in the low latitudes, that water is layered according to density. And it will stay that way because we don't have a giant hand to come shake up the, salad dressing. Thank goodness. And so where we have a thermocline, a region of rapidly changing temperature, we will also have a pycnocline, a region of rapidly changing density. Now, if you guys remember where I said it was really cold at the surface and really cold at depth, and it was that straight up and down line where we didn't have a thermocline, okay, that's uniformly cold, dense water. And what's really important about that, though, is when we make saltier water, it's going to sink. And this is what's going to happen at the higher latitudes. Up in the polar regions is where we're going to make deep water sink when we make that seasonal ice. And deep water is going to sink, and that's really important to sink deep water because it's going to take oxygen back down to the deep ocean. All right, so it's just the mirror image because remember, warm surface waters are the least dense, where the deep water, which is cold, uniformly cold, is the most dense. So if you have a pycnocline, you have a thermocline. It's a region of rapidly changing temperature. So we have both of those in those low latitudes. And we have uniformly cold, dense water up in the higher latitudes. So Santa has cold surface waters. All right, so we actually have the ocean layered according to density, and there's actually 3 different layers here. The first layer is called the mixed surface zone, or the surface mix zone. It's got the sun beating down on it, so warming it up, making it less dense. We have lots of good mixing going on: waves, tides, winds, surface currents. It's in contact with the atmosphere. It's got a good concentration of oxygen in it and other dissolved substances, gases. And this is going to range from the surface to about 300 meters deep. Okay. Then the next layer down, where we have a thermocline, it's called the transition zone. Okay, so remember that the thermocline and the pycnocline were regions of rapidly changing either temperature or pressure. This ranges between 300 meters and 1,000 meters. And this is well developed in the low and mid latitudes. And this region is going to stop vertical movement of water, either up or down. All right, when we get to the deep zone, it's uniformly cold. Now, even if you had the world's best light meter, if we took you down to 1,000 meters below the ocean sea surface, not even the best light meter in the world would pick up any light. It's completely dark. No light energy reaches there. Okay, it's cold. It's just like 2 degrees Celsius, and it's very dense because it is so cold. All right, look at this now. You guys notice the surface mix zone and the transition zone don't go all the way to the polar regions. The polar regions, you got those deep waters. And so most of the ocean is that deep zone. And we spend a lot of time talking about these surface mix zones. We're going to talk about them some more. But the deep water is so important. And if you get the chance to see that Day After Tomorrow, it talks about Countdown to Death of the Ocean. And they're talking about, that deep zone basically is if we don't sink those surface waters from the polar regions, which you can see in the purple on the far right and the far left, we don't return oxygen to the deep water. If we don't take oxygen down to the deep zone, it goes anoxic. If you've ever driven by a lake that's going anoxic or oxygen free, everything's dying and it smells awful, and yeah, it's not really pleasant. The layering of the ocean is kind of important.